On behalf of CSIR, I extend a very, very warm welcome to all of you who are attending this second episode of Innovation in Action. Innovation in Action is the new exercise that CSIR is venturing into with the main objective of reaching out to the society, the general public, the students, youth, job seekers, job providers, technology seekers, technology providers, and also all the ministries, departments, and the industries, MSME, startups, and entrepreneurs. Meaning is this is one platform wherein we are coming up with the introduction of different labs of CSIR. The lab director will appear and he or she will explain the unique, important, and the critical reasons due to which the society should have curiosity to learn about that particular institute. And in that series, first we listen to one laboratory, Central Building Research Institute from Roorkee. And today in the second episode, I take the pleasant privilege of introducing and welcoming the director of Central Glass and Ceramic Research Institute, Dr. Vikramajit Basu, who is joining us and who will take us through the journey of understanding the various accomplishments, the meritorious capabilities, and the unique strengths with which this lab is finding its relevance both in the national as well as in the international level. The main objective, as I told you, I'm just repeating with the very specific intention that this episode and this platform is offering a unique opportunity to each and every one of you to understand why this lab is important to this country and why this lab is important in the global perspective also. Now, with this brief introduction, Dr. Vikramajit Basu, please join online and make all the listeners and the viewers to get completely enriched about your laboratory for its every possible dimension of technology and scientific entrepreneurship. Now, platform is yours. Thank you so much. Namaskar.
Namaskar. Good afternoon, everybody. At the outset, I wish to express my sincere gratitude to Dr. N. Kalai Selvi, Director General of Council of Scientific and Industrial Research and Secretary DSIR, Government of India, to create this unique platform, which essentially allows us to showcase all the technologies that individual CSIR lab has created so far, and what is our aspiration as India marches towards Viksit Bharat, a developed India, by 2047. At the same time, I also welcome all the viewers to enjoy the different technologies that we have developed with the persistent efforts of a number of scientists and technical officers, technicians, technical assistants of the 75-year-old Institute of CSI. Having said this, my plan of the talk is as follows. I'll quickly introduce India as an emerging innovation leader. This will be followed by CSI CTCRS rich legacy, vision, and strengths. Then I'll share with you the CTCRS technology landscape. I'll also mention some of the key beneficiaries, societal services, and youth-specific contributions. Towards the end, I'll show you that how CSI CTCRI has contributed so far and will continue to contribute to lead the translational ecosystem in India and beyond. And I'll conclude my talk with an open invitation to the broader and larger society of the country and the world. Now, coming to India, now if you look at that India's progress, India's development in science, technology, innovation landscape, in the pre-independence period, it was largely driven by individual excellence, with Sir C.V. Raman winning the Nobel Prize for Raman spectroscopy, and several other scientists from different parts of the country has really excelled in innovation and innovation in the scientific world. Then coming to the post-independence, India has seen early industrial growth with the establishment of steel plants, as well as the establishment of Indian Institute of Technologies in different parts of India. In the 1970-1990, this is the period of technology-driven S&T, science and technology, followed by 1990s IT generation and global R&D excellence. Now we are in the era of extreme national and global relevance, and what our Honorable Prime Minister Sri Narendra Modi explained it as Atmanirbhar Bharat, which is a precursor, which is the way that this country will become the Viksit Bharat or developed India. Now, I'll share with you some of the interesting data. If you look at the gross expenditure of R&D in several other countries, European countries versus India, if you look at the European countries and some of the developed Asian countries like Japan and South Korea, it is 70 to 80% of the funding comes from industry. But in India, the trend is just reversed. Here, close to 60% of the funding comes from government, as well as less than 40% of the funding comes from industry. India's gross expenditure on R&D has increased by 3 times during the last 10 years, and is currently 0.64% of GDP, one of the lowest among all the fastest growing economies in the world. And what is the way forward? Suitable model for public-private partnership, which our Honorable Minister of Science and Technology, Dr. has emphasized in a number of public addresses, followed by equitable innovation system, startup ecosystem, and state-level innovation system. I'll take this opportunity to present some of the data. India ranks 3rd global in terms of number of publications, ranks 9th in Nature Index, and ranks 6th in the number of patents, and ranks 3rd in terms of number of PhDs in science and engineering. This is an interesting plot where around y-axis global innovation index is plotted, along the x-axis GDP per capita. Each country is represented here as a small to larger circle. The darker color essentially means that country is innovation leader. If you look at India's position here, it is one shade below the green shade. What it means that India has been performing consistently above expectations for the development that this country has witnessed over the last 14 to 15 years. Now, if you look at some of the data here, in terms of the researchers per million of citizens, according to the UNESCO data, India has only 262 researchers per million of citizens of India, millions of citizens of this country, whereas China is 1,600 and United States is 4,800. USA's R&D expenditure per year is 3.43% GDP, which is more than 5 times higher that of India. On a global scale, India is currently 38th place in GII compared to 81 place in 2015. So last 11 years is a massive progress. Onishanda National Research Foundation's budget is around $1.04 billion US per year. And just to give you some idea, MIT in the United States or Harvard in the United States, their annual research budget is around 1.4 or 2.3 billion US dollar. TU Munich, one of the best TUs in the Germany, this has 2.2 billion US dollar per year. Innovation. What is innovation? According to my understanding, innovation is an outcome of the process of integrated thinking. We need to create a unique R&D ecosystem which Council of Scientific and Industrial Research provides in our country, and innovation must have societal and economic impact. Now, if you look at this unique ecosystem that CSI has created since its inception, since it was established in 1942, currently there are 37 national laboratories from north to south, east to west of this great country, India, with 39 outreach centers and innovation complexes, where more than 10,000 plus dedicated scientific and technical staff have been working in diverse activities spanning from deep ocean to space exploration. Coming to CSIR, just introducing our institute. This is the Central Glass and Ceramic Research Institute, which was established as one of the first 5 national laboratories in this country in 1950. And it has now 2 outreach centers, one in Purja and one in Naroda. In terms of key performance indicators, for the last 25 years, it has developed 65 technologies, out of which 55 have been licensed, and it has 389 patents. This is by all means only national lab with core competence in ceramics and glass for technologically challenging applications. Its 2 outreach centers, they mostly contribute to regional socio-economic upliftment of traditional ceramics. In terms of numbers, it has more than 300 full-time employees, including 87 scientists. The external cash flow is one of the key performance indicators of any CSR institute. In 2025-26, it is close to 30 crore INR, which is close to 3 million euros. Now it has 9 R&D divisions in this institute, and these R&D divisions, they develop cutting-edge technologies based in Calcutta. And these particular, all these R&D divisions, they actually contribute to different key areas of national and global relevance that I'm going to mention in a few minutes or so. What is the institutional mandate? Our vision is guided by the IDEA principle, where I stands for inspiring the next generation of scientists. Capital D stands for delivering to the nation. E for engaging with the key stakeholders. And administration, it is rationally regulated facilitation, ensuring efficient, transparent, and excellence-driven administration. Our mission is to position the 75-year-old institute as a world-leading institute in ceramics, glass, and advanced materials, while accelerating innovation in transformative technologies to deliver positive economic and societal impact for India. Our leadership, we have 3 clusters. They are headed by our senior scientists. We have 2 outreach centers, as I mentioned before. We have chair, divisional chair, and associate chair. Their term is typically for 2 years duration. And then also, in order to promote some of the cluster activities, we also have scientists who are actually looking after 2 of our ceramic cluster, Morbi, and another in the state of Gujarat. CSR has, according to my understanding, it has 5 pillars of excellence. One in healthcare, strategic and national security, industrial infrastructure, energy and water. What I'm going to do in next 15 minutes time or so, I will go over each of these pillars of excellence, and then I'll also show you what this individual pillar has, what we have contributed under this individual pillar. Before that, let me also tell you that one of the major ideas of CSIR is to work in the mid-TRL to high TRL level, where in the left-hand side, academic institutes, they work in the early TRL, and then also blue sky research, whereas industry is in the other side of the bridge, and then CGCRI or CSIR technologies essentially bridge this gap, what we call its translation value of depth. And value of depth, this is unique. It is uniquely important, and that places CSIR as a whole very uniquely in the Indian science and technology landscape. So I'll go over, as I said, I'll go over individual pillar now. First one is healthcare. What is the tagline is innovating today for healthier tomorrow. Here, our key stakeholders are multiple industries. They are essentially multinational corporates like Sarjiware, and then at the same time, there are also few startups what we have transferred our technologies, or we are working closely. We also work closely with academia, R&D, labs, and regulatory agencies like CDSCO to get all the approval for our medical devices. Each of these pillars of excellence is uniquely positioned to be aligned with the United Nations Sustainable Development Goals, which are also mentioned in this particular slide. Now, let me give you some examples of the unique technology or signature technologies that this institute has developed. First one is Liponat and alumina-based ceramic X as articulating components for total hip joint replacements. And this particular technology has been transferred a few years ago to Sarjiware that is based in India. Now, let us see this video.
For millions suffering from severe hip joint damage, even simple movement can become painful. Traditional metal implants can wear out over time, causing discomfort, friction, and repeated surgeries. Now, India is developing a smarter solution. CGCRI has developed advanced 5th generation zirconia toughened alumina ceramic hip implants. Designed for superior strength, better wear resistance, reduced squeaking, and longer implant life.
CSIR CGCRI Kolkata has developed zirconia toughened alumina composite based total hip replacement material for hip joint replacement application. It has two parts. One is acetabular cup, one is femoral head. The technology for manufacturing of this is transferred to Surgiware. It is a UB-based, very popular company, and property-wise, it is far better than even the important one.
These implants are manufactured with flawless polish and precise sphericity for smooth articulation and better movement. Fully matching ISO and ASTM standards, this technology delivers globally competitive quality. And with costs reduced by more than 50% compared to imports, advanced healthcare becomes more accessible. This is more than an implant. It is science improving mobility, independence, and quality of life.
So next technology is that Neopic, this polyheptatone. This particular composite material, which is essentially radiolucent and antibacterial in nature, has been developed in this laboratory, and which is essentially used for spinal reconstruction applications. We know L1, L2, L3 in the spine region, and there this particular material can be inserted, and which will help in the spinal fusion. What is the current status of the technology? What we call Neopic TN. It has gone through many of the mandatory regulatory compliance testing at the NABL accredited laboratory that has been mentioned. And these particular materials is machinable, it's 3D printable and injection moldable, and then gamma sterilization is one of the techniques that will be used for packaging and for the clinical applications. Next one, I'm going to show you some of the applications of the laser. But before that, let me also show you this kind of unique facilities that this particular institute has in the area of the fiber laser or glass fiber with tailored chemistry sizes. This is the modified chemical vapor deposition, which allows the vapor phase shielded delivery system, and then also the diameter of the fiber can be tuned over 10 to 18 millimeter. That's a preform diameter. After that, you can draw. This is a tower. This is a two-story building tall fiber tower, which allows the fiber diameter also to increase to 80 to 400 micron. And you can see that at the core, where this silica-based glass fiber, which can be doped with different rare earth elements, that is surrounded by the cladding and then also the coating at the final outer layer. Typically, the core diameter is, if it is a single core fiber, it's a 9 micron diameter, whereas the total diameter of the glass fiber with coating is 125 micron. Now, based on this thulium doped silica-based glass fiber, we have developed this thulium fiber technology, which has been clinically validated to break the stone in the kidney or uterus in different organs in the human patients at different multi-centric clinical trial centers in this country. And Allengers is our technology transfer partner, and Allengers have taken this technology to different laboratories within India. And this is one of the success stories of CSR-CGCL. We also have developed several other technologies we have not yet transferred to the industry. One such technology is BreathPeak, and this is a non-invasive diabetic breath analyzer. So traditionally, we can use different techniques like glucometer, which is very easily you can draw, you can pick the blood and then you can put it, and then instantly you can essentially get the data, what is the fasting blood sugar or PPPS. But diabetic breath analyzer works in a different principle. It actually takes exhaled breath of a patient based on the acetone content in this breath. Essentially, they can classify the patients whether it's a pre-diabetic or diabetic patients, and this particular table essentially gives you some quantitative ideas about what I just mentioned. And its USP includes painless monitoring, rapid responses, and advanced nanotechnology-based repeaters innovation has been utilized, and it can be IoT integrated. Now, coming to another societally relevant technology is for the female sanitary hygiene applications. This is again polycaprolactone-based electrospun fibers with zinc oxide and many other elements that has been added to develop, to manufacture the top sheet, which has been tested in the regulatory compliant facilities at Sichita University of Medical Science and Technology in Trivandrum, both for antibacterial and antifungal tests. And also we have done biodegradation studies in the landfill conditions to see how this material can be degraded in the post-use conditions. Now moving to pillar 2 is the strategic and national security. And here we innovate for a secure and safe, reliant, and resilient India. The first one, what CGCR is also equally famous for the ceramic radomes. And in the electromagnetic window, in the radome metal need to have a very low dielectric constant and low loss standard. It is not every ceramic metal will qualify, but we have developed a technology for the reaction button silicon nitride, which has been supplied to research center Imara DRDO. They have qualified, and then we are now given another challenge to develop the atoms for the Kusha missile, and this is for the very largest size that our CI wants. And then we have also compared or benchmarked the properties the CGCRI atom has with that of the global benchmarking, and most of the properties are again benchmarked quite well. CGCRI has been serving the strategic sector for a long time. This is another example that we have been supplying, or we have been collaborating with the Raja Ramana Center for Advanced Technology Indore, Anakat Indore. This is the requirement for niobium low phosphate laser glass for high energy, high power applications. We have the capability to develop these glass materials in different blocks and different rod sizes, and these are essentially used for edge cladding glass to absorb the radiation at lasing wavelengths. And this is the underlying physics is essentially radio refractive index is equal or slightly more than that of the lasing material. And in all these cases, we also carefully evaluate the performance in terms of the homogeneity or interferometer pattern.
Hi, this is Dr. Akhil, scientist here working at the division of CSR Central Glass and Ceramic Research Institute. We are going to present very important critical technology we have developed over the last 4-5 years, and this is basically a glass ceramics. We are going to present a really important critical technology developed for our defense sector. So through this video, we'll show the product and its applications.
At the CSIR Central Glass and Ceramic Research Institute, we are redefining this standard. We are engineering a solution to make bullet-resistant glass lighter without ever compromising on protection. Our team has developed an advanced glass ceramic material, meticulously crafted by integrating glass with nano-sized ceramic crystals. The result? A material that is significantly thinner and lighter, yet possesses extraordinary impact resistance. In rigorous initial testing, this innovation successfully withstood high-velocity rounds fired from an AK-47. The applications are transformative, from bulletproof vehicles to military helicopters to critical naval platforms where every kilogram matters. More importantly, this breakthrough is a pivotal step in India's journey towards self-reliance in critical defense materials. In essence, we are making the future of protection lighter, stronger, and harder to break.
Okay, this next innovation in the field of glass material is the chalcogenide glass for thermal imaging applications. What are these chalcogen elements? This is sulfur, selenium, and telluride. This is group 6A of the periodic table elements in conjunction with some of the electropositive elements from group 4A or group 5. So these particular chalcogenide glasses has been fabricated in different sizes, and particularly 30 to 100 millimeter diameter and 10 to 25 millimeter in thickness. What is the USP? That these glasses have been used for transmission up to 14 micron, and then also these particular glasses is arsenic free. These properties are clearly matches with that of the Short glasses. Short is a company in Germany which has been several hundred years old, and they are in the glass business for many, many years. We have supplied to BEL, Bharat Electronics Limited. They have fabricated a thermal imaging camera we have received the satisfactory performance report very recently on the chalcogenide glasses. Next one, space quality optical glasses for Indian Space Research Organization. This is the recent glass technology that we have developed, Sudarshan Optics 603. We have the capability of the glass melting at different temperature, and then also bottom boring and then field casting facility that we have. These glasses have been made in different blocks of different sizes. One of the most important things is the homogeneity, and we have been able to achieve the homogeneity of 10⁻⁶ order, and which is exactly what ISRO wants us to deliver, an average retardation of 0.89 nanometer. Its manufacturing has been established in 100,000 class clean room, and as I say, 10⁻⁶ order homogeneity, which is equivalent to again the German glass company short, and this is undoubtedly one of the most important achievements in the recent years from this lab. Is coming to continuous wave fiber laser. This is manufactured is using another rare earth dopant. This is that that ytterbium fiber, ytterbium doped laser fibers, and there are two particular areas. This particular laser has been shown in promise. One is the metal sheet cutting, and this particular the performance has been tested. The Tajanan company, one of the major manufacturers of the state. So bottom on see this has sister lab, DMLA Durgapur, and this is for the laser contribution based application for additive manufacturing. And the next the metal component that we have been able to fabricate. Moving to pillar number 3 is the industry and infrastructure. We build capabilities, we enable growth to strengthen our very nation, India. First one is that we have been leading one of the major national program that is Center for Innovation and Manufacturing Ecosystem for Sensors, which we call it briefly is the CMS. This particular center has been funded by METI. So fiber gravitating sensors, this is also a unique component, unique competence of our CSIR CGCR, right? Essentially, this video is not well. So essentially what we do, we use the glass fiber, and this glass fiber, we essentially use the UV beam to inscribe at a particular length. Now, depending on the distance between these two beams, there was this inscribed line. It actually helps us to sense whether it's temperature, whether it's vibration, whether it's tilting phenomena or displacement in particular application. Now, you see that 3 of our sensors, tilt sensors, vibration sensors, strain sensors, at different level of technology readiness level, either TRL5 to TRL7. In the next slide, I'm going to show you that field trial that has been accomplished with 2 such sensors. One is the vibration sensor that has been tested in a viaduct in metro station in Bharat. And this particular sensor has allowed us to get real-time data during the field trial. The second field trial has been done in Mangalore Railway Bridge, and where again we have been able to record all the output data in terms of counting, wheel counting, bogie load, number of bogies. Tata Steel. Now, Tata Steel actually has been producing about mild steel for a long, long time. Now, in the past, many times the problem is that in the continuous casting process, when the liquid metal is poured at 1600 Celsius, and we have not been able to control the mold through which this liquid metal is passed through before it is being shaped into slabs, then there is a rupture in the mold, what they call breakout event that takes place. So therefore, mold temperature monitoring and then also control is one of the key things prevent a lot of economic loss. So what is the USP of the fiber wrapping LPG sensors? Is the temperature measurement spatially at different locations along the mold. And this particular technology has been employed in Tata Steel. And you can see in the real life demonstrations that how the temperature has been monitored and recorded using our sensor. This technology has been transferred to a startup company which has supplied these temperature sensors to Tata Steel. Moving to pillar 4 is the energy. Energy is one of the major pillars in terms of CPCR's capabilities in the national landscape. So first one is the solid oxide electrolyzer.
India is redefining the global energy landscape through the power of green hydrogen, targeting 25 gigawatt of electrolyzer capacity by 2030. Our mission is clear: transition to a low carbon economy. By optimizing green steel and ammonia production, we aim to drive hydrogen cost below $2 per kg. Rapidly expanding global and domestic markets are unlocking massive industrial opportunities. Our solid oxide electrolyzer technology lead with a high current density of 1.5 amps per centimeter square at 800 degrees centigrade. Utilizing patented roll-to-roll manufacturing and noble electrode materials, we ensure robust, scalable, and highly efficient production. Through the CSIR CGCRI, QME, and Dense Power collaboration, we are moving from lab breakthroughs to real-world system. Our roadmap scales from kilowatt-level pilot to a modular system exceeding 100 kilowatt for industrial deployment. We are systematically overcoming cost and operational challenges through focused engineering. From material innovation to commercial field deployment, our technology is ready for the future. Together, we are securing India's leadership in the global green hydrogen economy.
So this is the story of the solid oxide electrolyzer technology, which have transferred to carbon nanometer Murugappa. This is the QME. Now the second technology is the preparator. It's a paper-based separator, ceramic separators for lithium and sodium ion batteries and supercapacitors. It has developed this unique technology where BaTiO3 barium titanate is integrated into the tri-layer paper separator of 20 micron thin, which has passed through flame-proof tester. And you can
Since
see
2004, CGCRI has been actively engaged in developing advanced ceramic-based electrode and solid electrolyte materials for world's most sophisticated rechargeable lithium batteries. High-end battery-grade electrode components are prepared with CGCRI patented processes and scaled up for battery application. In recent time, CGCRI developed a first-of-its-kind separator component for lithium-ion, sodium-ion, and supercapacitor applications. The developed paper-based ceramic separator has been named as Paperator and fabricated using in-house designed semi-automated machine up to a scale of 100 meter in length with flexible width. This Paperator showed flame retardant characteristics, which is an essential safety requirement for any battery. The developed ceramic-based cellulosic separator is a perfect low-cost alternative of commercial plastic separators and recognized as one of the 16 CSIR technologies with future market potential.
the last one in the energy pillar, under the energy pillar, is the photovoltaic assisted water splitting using bifunctional electrocatalysts. Now, this technology is based on metal ferrite oxide with polyaniline, and what we have shown that it has the capability of hydrogen production at the rate of around 50 millimolar per hour of the gram of the catalyst. Moving forward, it is our aspiration to create this technology with these photoelectrochemical photovoltaic tandem devices for efficient water splitting applications. We have also contributed to the safe drinking water, and then also for treating the groundwater, and then also for the agriculture related applications I'll show you in next few minutes. Now, ceramic membrane technology, we have a membrane separation technology division. They have developed alumina-based ceramic membranes, and essentially we are able to remove both arsenic and iron for the groundwater. The fundamental scientific background is that this arsenic iron is being oxidized, and these actually form a stable flux, which are very easy to be passed away through this microfiltration technique or the design porosity that this particular ceramic membrane have. Now, arsenic is one of the major impurity content, and that has been removed below the WHO, that World Health Organization limit, and this we call is a safe drinking water. With the help of in collaboration with CSIR NIST and Prism Johnson Limited, we have also deployed our pilot plant at different locations in India. One of them is a northeastern state in the Meghalaya and Shillong, iron removal plant in the Shillong Science Center, and then also different parts of India. More than 200,000 citizens of India were benefited with this particular CSR technology. Now, moving to circular economy approach for the micronutrient enriched rice. CSIR has a unique program, Waste to Well. Under the Waste to Well program, we have utilized the jute waste. We have converted to the surface engineered biographene, and which is being used as a substitute for the commercial activated carbon. Now, what we have done in this biographene, we have loaded with zinc, and then we have the pilot scale production of 25 kilogram per batch of this biographene-based zinc microfertilizer. When we have the when we have done the field test in the state of West Bengal, what we have seen that both the crop yield has been increased, and then zinc enrichment is rise has been recorded post few months. And you can see in this field trial, at the day one, the crop is started growing, but the 3 months is a fully developed crop has been observed. And then also we have recorded the soil enrichment. This particular technology has been validated for rice, but this can be also extended to other food items as well. Now, futuristic and emerging technologies, some of the things that we have already started, and it is our aspiration that we will actually travel quite deep to explore these technologies for the future of the mankind. One of these computational material science, semiconductor and quantum technologies. I'll show you one such example. In the glass science, we utilized around 330,000 composition, because glass, as you know, is a multi-component oxide material which is non-equilibrium in nature and which has also a glass transition temperature. So by varying the composition, the properties of this glass can be also tuned within certain window. And what we have done, we have not only utilized this 330,000 composition library, but we have also developed this Sigma platform, what we call AI research platform, where 120 properties of this glass, including elastic fiber strain and many other properties, can be predicted.
First, choose the glass composition. Like SiO2, you can see a PnPO3 and CO will have selected. Now select one of the properties for those compositions. Okay. Now it will show all those glasses that have those compositions along with their clusterness temperature. Now next, instead of one properties, if you want to calculate multiple properties from that given glass compositions, now we have selected the compositions. Now you can select multiple properties from here, like clusterness in temperature and also Young modulus, but you can select up to 20 and it will show all those properties could have been, like you can see that clusterness in temperature and also it is showing that Young modulus put there. And here we get the some that compositions from where it was collected in details.
Right. So we have also new R&D section called Emerging Quantum and Semiconductor Technologies. We have got few projects very recently. One is in the area of quantum biosensors, where Department of Biotechnology is funded for these ultra-sensitive multimodal biosensors. Another one that we have been working on is superconducting platform. So in the semiconductor ceramics, we are working with a project with applied materials. Very recently, I've given a Ignite talk of the applied materials. So where we are essentially developing aluminum nitride bulk ceramics using spark plasma sintering, and these aluminum nitride ceramics also can be fabricated using tape casting process. And one of the major challenges in the tape casting to develop tape without any cracks, and is also fully sintered. And there we have formulated an optimized slurry composition with 50 to 70% solid loaded slugs. Moving forward, our security is very important, country security is very important. What we plan to explore is a blue-green laser for underwater surveillance applications. And here, we plan to take this project further in next few years' time, where we can see that blue-green light, which is a much higher penetration than any other combination of the laser, that can be successfully developed and also deployed, and technology can be validated with the help of our CSIR sister laboratories. Next one is the in situ synergistic magnetoacoustic laser for cancer regression, with the use of the synergistic application, very small magnitude static magnetic field of 100 to 300 millitesla, and then also ultrasound. With these two different biophysical stimulation, our scientists have shown that in the rat model, breast cancer tumor can be regressed over 3 weeks of this iSmart stimulation, iSmart simulation-based technologies. And this particular technology, we are considering to take it forward further with the IF MedTech, that's a Mumbai-based company, which is also participated in our recent activity. Now, unique societal services, skill development programs, as I mentioned in the beginning of my lecture, that 2 of our outreach centers, Purcha and Naroda, that have been contributing over last several years to different skill development activities, and then also training activities in the bone china waste recycling, wiper cluster development, where the Naroda Center has been closely collaborating with Mordi clusters and Thanagar clusters based in Gujarat. And they have been also giving the training on terracotta or terracotta glazing techniques or terracotta jewelry applications. In terms of the CSIR's flagship program, Jigyasa, we have been starting a new initiative that we have been organizing district level as opposed to school level programs, and that has impacted more than 1,500 boys and more than 1,800 girl students in different districts in the year 25-26. We not only inspire the students, but also we inspire the school teachers in all these district level events that we have organized over last 1 year. One day as a scientist, this is also another flagship program, as our Honorable Prime Minister has also mentioned in the Mon Ki Baat. And there also we have actually, we had a major program where large number of students from different parts of West Bengal participated very recently. CSIR right? This is the only national lab of importance in the area of ceramics and glass. That has been working very closely with other CSIR sister labs, ESP labs, DPT labs, or ICMR labs over last several decades. It has been a very close friend to strategic sectors, atomic energy, defense, and also ISRO, Space Research Organization. It has been also working with different testing and certification agencies, and also by contributing that what are the different test guidelines for example, Bureau of Indian Standards, and then also working with several companies, either co-development projects or we transfer the technology, where technology goes to different maturation stage before it goes to the market. In terms of global connectivity, we have been also talking to some of our colleagues in Germany, like Fraunhofer Institutes in Dresden, and then also we have been also providing some platforms of our Indian Ceramic Society and many other organizations. In terms of policy, we also feel it equally important that we contribute to the national policy and strategy papers in the field of biometrics. This is just 2 such examples, but recently one of our strategy papers has been also accepted in the Journal of American Ceramic Society on glasses. This is one such paper that has been published in Proceedings of Indian National Academy of Engineers on National Strategy Paper on Fiber Bragg-Gaping Sensors. This is an important slide, but it shows that over last several years of our existence, it has actually impacted multinational corporates, MSMEs in this country, and several of that have been mentioned in the left panel. Also, strategic sectors that I have mentioned at several points in last half an hour or so, and PSUs like by NTPC like BHEL, Bharat Electronics, and so on. Industry clusters, Morbi Ceramic Manufacturing Association, Morbi Ceramic Clusters, Pucha Ceramic Clusters, and Electronic City Industry Association, but based in Bangalore. We have signed an MOU, and many of our scientists have participated in two of the major brainstorming section. And the idea is that we take our technology through the LCA platform, the users in very soon. And startups like Ceramic, Universe, Veryline Labs, these are some of the startups that we have been working. And some of the startups have also got benefited through our technologies. Over the last 1.5 years, we have been interacting with several IITs. We have signed MOUs, one of the first generation IITs like IIT Kharagpur, IIT Madras, Board of Governors has cleared our MOU, IIT BHU, and so on. And then also, our next door neighbor is International Cultivation of Science. We are signing an MOU also with the cultivation of science. So with all these connectivity or engagement with the academic ecosystem, what we believe that CSR-CGCRI will continue to contribute both on the fundamental research, on the scientific discovery, as well as continue to work on this technology development and technology translation. CSIR has an innovation complex in Mumbai, and we have been also engaged. We have also actively engaged with this Mumbai Innovation Center. We have signed 5 MOUs with different companies, and more recently, we have organized another conclave called CGCRI Srishti in the month of July, and 3 major areas that we have identified. One is the battery or energy-related applications, where 3 of the companies, they have expressed interest, and we are signing an MOU, and then also fiber laser, for use of fiber bracket-getting sensors. And it is our aim to refurbish the CSIR Tabor Park Incubation Center in Kolkata, and that is coming up, and that will be spoke of that ICM Mumbai. Now, towards the end, I would like to reiterate our commitment for Viksit Bharat Vision 2047, and this will be our strategic role of CSR-CGCRI. We want to see a developed India, and this developed India will begin with indigenous materials powered by Indian ingenuity and scaled through the CSR ecosystem. And here, one of the constituent laboratories of the CSIR system, CGCRI, will bring in materials innovation, the technologies which no other national labs in this country can afford to deliver, like fiber bag-getting technologies and our unique glass manufacturing ecosystem and many other interdisciplinary research concepts and ideas. Together, we'll build a new India, that is Viksit Bharat, developed India, and which will be powered by Indian intelligence and scaled by the CGCRI ecosystem. We welcome all the citizens of this great nation, Bharat, and stakeholders in our journey to take innovations to society for Viksit Bharat. Thank you. Dhanabad. Namaskar. Jai Hind.
Thank you, Professor Basu. Maybe you can stop sharing the slide. Professor Basu, am I audible? Yeah, thank you, Professor Basu, for delivering this second lecture in our Innovation in Action lecture series. It was indeed an engaging session highlighting the many significant R&D contributions of CSR-CGCRI. Thank you to all our viewers for tuning in today. We look forward to bringing you the third lecture of the series very soon. Until then, stay connected